Hello everyone and welcome to our second lecture. Um, our today's topic is memory management in operating systems. So this topic is critical in understanding how operating systems efficiently allocate, manage and optimize memory resources for different processes. So by the end of this session, you'll have a clear picture um, of the concepts, techniques, and strategies employed in memory management. So let's begin with an introduction to memory management. So it is one of the critical functions of an operating system. It plays a vital role in ensuring efficient allocation, deallocation, and access of memory resources for applications. Without proper memory management, systems can experience conflicts, inefficient CPU usage, and poor performance. The purpose of memory management includes three key goals. One is optimizing CPU utilization. So this one is like excuse me. By providing quick and direct access to memory, it helps the CPU work efficiently. Second is preventing memory conflicts. This one ensures that multiple processes running on the system do not interfere with each other's memory space. Third is enabling multitasking and program execution. Memory management allows multiple applications to run smoothly at the same time without crashes. So, for example, think of your smartphone. You have likely switched between multiple apps at once, say watching a video, responding to a message, and checking your emails. So memory management ensures that these apps operate seamlessly without slowing down your phone or causing interruptions. So moving forward, let's discuss the concept of memory hierarchy and trade-offs. So memory hierarchy is a structure that balances speed, size, and cost to achieve optimal system performance. So different levels of memory serve specific purposes with trade-offs between their access, speed, and cost. So here are the main levels of memory hierarchy. First is registers. Registers are the fastest type of memory in a computer system, but also the most expensive. They reside within the CPU and are used to hold temporary data and instructions that the processor needs to execute quickly. Second is cache memory. Cache acts as an intermediate memory. It provides quick access to frequently used data, reducing the time the CPU spends fetching information from slower memory levels. Third is RAM, random access memory. RAM serves as the main memory of the system. Programs and data that are actively in use are stored here, enabling efficient execution. Fourth is secondary storage, like the SSD or hard drives. So this includes those hard drives, SSDs, and these are much slower but provide large long-term storage capacities. They are cost effective and used for persistent data storage. Now, as you move from register to secondary storage, you'll notice that while speed decreases, the capacity and cost efficiency improve. For example, registers are extremely fast but very limited in size, while SSDs and hard drives are slower but provide vast storage capacity. So understanding this hierarchy is crucial for designing efficient operating systems and hardware that balance performance and cost. This layered approach ensures that memory resources are optimized to provide the best possible performance for both applications and the user. So now let's look at the visual representation of the memory hierarchy in terms of speed versus storage levels. As you can see on the graph, registers are the top of the hierarchy with the highest relative speed, approaching 100%. These are embedded within the CPU and are extremely fast but also have the least storage capacity. Then cache memory. It offers very high speed close to registers, but it is slightly slower due to its larger size and location outside the processor core. Cache significantly reduces data fetch time for frequently accessed instructions. Then we have RAM. So RAM, as seen in the graph, provides a balance between speed and storage. While its speed is lower than cache, it has much greater capacity and serves as the working memory for active processes. And then lastly, secondary storage, which are much slower compared to the other levels. However, they offer massive storage capacity and are cost effective for long-term data storage. So this graph clearly highlights the trade-offs between memory speed and storage capacity. And understanding this trade-off helps optimize memory usage in operating systems, ensuring a balance between performance and storage efficiency. Okay, let's discuss contiguous memory allocation now. In contiguous memory allocation, processes are assigned consecutive memory blocks within the system's memory. This method ensures that all the memory a process needs is allocated in a single continuous section. There are two main types of contiguous allocation: fixed partitioning and variable partitioning. So the first one, in this approach, memory is divided into equal sized blocks or partitions. Each process is assigned one block. This method is simple and was widely used in early computer systems. However, it can lead to wasted memory if the process size is smaller than the block. Then second is variable partitioning. Here, memory is divided into dynamically sized blocks based on the needs of each process. While this approach avoids wasted space from fixed partitions, it can lead to fragmentation over time as processes are loaded and removed. So for example, like early computer systems used fixed partitioning due to its simplicity in implementation. However, as systems evolved, variable partitioning became more popular due to its flexibility and better memory utilization. Okay, non-contiguous memory allocation. So unlike contiguous allocation, non-contiguous memory allocation allows processes to be stored in scattered memory blocks. This provides greater flexibility and better memory utilization because the memory does not need to be assigned in a single continuous section. So non-contiguous allocation is implemented using two primary techniques. First is paging. Paging divides memory into fixed size pages. Each process is split into blocks called pages, which are then loaded into available memory frames. Since pages can be stored in non-adjacent frames, it helps avoid fragmentation issues that occur in contiguous allocation. Now next, Second one is segmentation, which divides memory into logical segments such as code, data, and stack. Each segment is of variable size depending on the program's structure. This technique aligns with how programs are logically organized and allows for efficient memory management tailored to the needs of different program segments. So, non-contiguous allocation solves many of the limitations of contiguous allocation by improving memory utilization and reducing fragmentation. However, it does introduce some overhead in managing scattered blocks and requires techniques like page tables or segment tables to keep track of memory locations. Now let's focus on paging in memory management. So as I said, paging works by dividing both the logical memory and physical memory into equal sized pages and frames. Each page in the process is mapped to a frame in physical memory using a page table. The page table keeps track of the logical to physical address translation. So there are some advantages of paging, which is first one is eliminates external fragmentation. So since memory is divided into equal sized unit, there is no wasted space between memory blocks, so it eliminates external fragmentation. Second is simplifies memory management. So the system doesn't need to allocate contiguous memory blocks. Scattered free frames can be used efficiently. But there are some disadvantages of also. So page table overhead, which is like when a page table needs to be maintained for each process, which adds some overhead. Second is possible internal fragmentation. So if a process does not fully utilize a page, the unused space within that page is wasted. For example, if the page size is 4 kilobyte but the process only needs 3 kilobyte, 1 kilobyte remains unused. So we can say that paging solves the problem of external fragmentation, but at the cost of maintaining page tables and dealing with internal fragmentation. This trade-offs is acceptable in modern systems due to its flexibility and efficient memory use. Okay, now we'll see a real-life example of paging to better understand. When you switch between apps on your smartphone, the operating system uses paging to efficiently load and manage memory. Here's how it works. When an app is actively in use, the required parts of the app are loaded into physical memory or RAM. Portions of the app that are not immediately needed, such as background data, remain stored on the disk or storage. If you switch back to the app later, only the necessary pages are brought back into memory, ensuring efficient memory utilization without overloading the system. For example, if you're using a messaging app and then switch to a video streaming app, paging ensures that both apps remain accessible, but only their active components are loaded into RAM. This minimizes memory usage and allows for smooth multitasking. Now let's see segmentation. So segmentation, as I said, divides memory into logical segments based on the structure of the program. For example, a program can be divided into code segment, data segment, stack segment. Code segment contains the program instructions. Data segment contains it stores the program's data. Stack segment manages function calls and temporary variables. Each segment has a logical address, and these addresses are mapped to physical memory using a segment table. This table keeps track of the segment number, base address, and length. Advantages of segmentation. So, segmentation aligns with the natural structure of a program, making it intuitive and easier to manage. So second is easier memory sharing. Segments like code can be shared between processes, reducing memory duplication and improving efficiency. So there are some disadvantages also. So first is external fragmentation. Since segments are of variable size, gaps can occur between memory allocations, leading to external fragmentation. And then second, managing segment tables and handling variable size segments adds complexity to the memory management system. So there's complexity in implementation. Okay, let's see a real world example here. In modern web browsers, each table you open represents a separate process, and within each tab, memory is divided into logical segments. If you say HTML segment, CSS segment, JavaScript segment, these are the code segments. So the HTML segment contains the structure of the web page. CSS segment, it is a separate segment, handles the styling, ensuring the page visual presentation. JavaScript segment, another another segment is responsible for the interactive behavior and scripts running on the page. So by using segmentation, browsers ensure logical separation of these components. This separation helps in two main ways. It allows efficient memory handling of different tabs, even if one crashes, ensuring other tabs are unaffected. It enables better memory management and resource allocation for the browser as a whole. Now here is a graph showing the comparison of paging and segmentation, which evaluates their performance based on three key attributes: efficiency, flexibility, and fragmentation. So if we talk about efficiency, paging represented by the blue bar scores higher in efficiency. This is because paging eliminates external fragmentation by dividing memory into fixed size pages, making allocation straightforward and efficient. Second is flexibility. So segmentation shown in the orange bar is more flexible. It divides more into logical segments that align with program structure, such as code, data, and stack. This flexibility allows for better management, memory organization, and sharing. Third is fragmentation. Paging has an advantage here as it is minimize external fragmentation. However, segmentation suffers from external fragmentation due to variable sized segments. Okay, so now let's discuss virtual memory and demand paging, two critical concepts in modern memory management. So virtual memory extends RAM by using disk space to enable larger address spaces for programs. It allows systems to run applications even if they exceed the physical RAM capacity. So these are the techniques used for virtual memory. First is paging. Virtual memory uses pages to manage more memory efficiently. Then second is demand paging. This technique loads pages only when they are needed. So pages are loaded on demand, meaning they are not preloaded into memory but accessed only when required. This reduces the physical memory requirements as only the active portions of a program need to be stored in RAM. So there are some benefits also. First is it supports larger address spaces. So programs can access more memory than what is physically available, and it reduces physical memory dependency by utilizing disk space for inactive pages. RAM usage is optimized. So for example, if you think about running multiple applications on your laptop, even if the physical RAM is fully utilized, virtual memory allows the system to keep running by temporarily moving inactive portions of programs to disk space. This ensures the applications run smoothly even beyond the limits of physical RAM. Okay, let's now talk about swapping in multitasking, an essential technique in memory management for freeing up memory. So, what is swapping? Swapping involves moving inactive processes from RAM to secondary storage like a hard drive or SSD. This frees up memory space so that active processes can run efficiently. So here are the steps how it can be done. First is identify inactive processes. So to move in any inactive process, first we have to identify. So the operating system detects which processes are currently idle or not needed immediately. Then it moves their data to secondary storage. So these inactive processes are written to disk, freeing up space in RAM. Then reload data when required. If the process becomes active again, its data is reloaded from the secondary storage back into RAM. So these are the steps we can use. For example, like in multitasking environments such as desktop operating systems use swapping extensively. For instance, when you open multiple programs on your computer, the operating system may swap out background processes to disk to ensure active applications have sufficient memory. This allows you to work smoothly across multiple tasks. So the key benefit of swapping is like it enables efficient multitasking by managing memory dynamically, ensuring that system performance remains optimal even when resources are limited. Okay, fragmentation. So there are some types. There are two types of fragmentation: internal and external. So the internal fragmentation occurs when the allocated memory block is slightly larger than what the process actually needs. For example, if a process requests 3.5 kilobyte but memory can only allocate a 4 kilobyte block, the remaining 0.5 kilobyte is wasted. This small unused space within allocated memory leads to internal fragmentation. So then external fragmentation happens when free memory becomes scattered across different locations, making it unusable for processes that require larger continuous blocks. For example, frequent allocation and deallocation of memory can create small gaps between used memory blocks, which cannot accommodate larger processes. Now, what are the solutions? First is compaction. So, it is a technique where the operating system shifts memory blocks to consolidate free memory into a single large block. While effective, this process can be time consuming and requires system overhead. Second is non-contiguous memory allocation, like techniques like paging and segmentation, which help avoid external fragmentation by allowing processes to use scattered memory blocks instead of requiring contiguous memory. So this is the visualization of internal and external memory allocation. Internal and external fragmentation. Here memory blocks are allocated to processes, but there's some unused space within each block. For example, in block 2, the process uses most of the memory, but a portion remains unused. This occurs because the block size is larger than what the process requires. So the orange segments in the graph represent the unused space caused by internal fragmentation. On the external fragmentation, a memory is scattered, creating free spaces between allocated memory. So if you look at block 1 and 2 have free space, but the scattered gaps make it impossible to allocate a larger process. Even though the total free space may be sufficient. This is a classic example of how external fragmentation leads to inefficient memory usage. So let's now highlight the advantages of virtual memory and why it is essential in modern computing. So first is execution of programs larger than physical memory. So virtual memory allows programs that are larger than the available physical RAM to execute smoothly by using disk space as an extension of memory. This is crucial for running large applications and multitasking. Second is enables multitasking and efficient memory utilization. So virtual memory supports multitasking by dynamically allocating memory to active processes and swapping out inactive ones. This ensures efficient memory use and prevents the system from running out of physical RAM. If you take gaming PCs as an example, so modern video games often use large textures and data files that exceed the physical RAM capacity. So virtual memory enables the system to handle these large resources by offloading less critical data to disk storage, allowing the game to run seamlessly. To better understand the virtual memory, let's look at a real life scenario involving Google Chrome. So a user has multiple tabs open in Google Chrome. So how virtual memory helps? So first of all, active tabs, like tabs that you're currently using, remain in RAM for quick access, ensuring a smooth user experience. Then inactive tabs. Chrome uses virtual memory to move inactive tabs to disk storage or swap space. This process frees up RAM for inactive processes and ensures your system remains responsive. Third is benefit, like users can keep many tabs open without the system slowing down. Virtual memory efficiently manages memory by offloading inactive data to the disk. For example, like if you switch back to inactive tab, you might notice a slight delay as Chrome reloads the tab. This happens because the tab's data is being fetched from virtual memory, not RAM. Okay, trashing in virtual memory. So, trashing occurs when the system spends excessive time swapping pages in and out of memory rather than executing processes. This happens when virtual memory is overwhelmed, leading to constant disk I/O operation. So, what causes of trashing? What are the causes of trashing? First is insufficient physical memory. So, if the available RAM is not enough to accommodate active processes, the system relies heavily on virtual memory, causing frequent page swaps. Second is overloading the system. Running too many processes simultaneously can overload the memory, forcing the system to swap pages repeatedly. So, what are the solution to trashing? So, it increase RAM. So increased RAM is one of the solution. Like adding more physical memory reduces dependency on virtual memory, allowing the system to handle more processes efficiently. Second is we can optimize workload and adjust page size. Like balancing the workload by reducing the number of active processes can minimize memory pressure. Adjusting the page size in virtual memory can also help reduce the frequency of page swapping. So, trashing significantly reduces system performance because the CPU spends more time swapping pages than executing processes. By addressing the root causes such as insufficient memory or overloaded systems, we can prevent trashing and ensure a smooth system operation. Okay, so this graph illustrates the impact of trashing on system performance as the paging intensity increases. If you see on the y-axis, we have system performance ranging from 10% to 80%, and on the x-axis, we see paging intensity categorized as low, mid, moderate, high, and excessive. So at low paging intensity, system performance is high, around 80%, as the system efficiently manages memory. As paging intensity increases to moderate, performance begins to decline, dropping to approximately 50%. This indicates that more time is spent swapping pages. Then at high paging intensity, the system struggles further and performance reduces sharply to about 30%. Finally, at excessive paging, performance drops drastically to nearly 10%. At this point, the system is experiencing trashing, where it spends almost all its time swapping page instead of executing process. Okay, now let's see memory protection techniques and why they are crucial for operating systems. So why it is important? So first of all, it prevents unauthorized access to memory. Well, memory protection ensures that one process cannot access or modify the memory or another process. This is critical for data integrity and system security. Second is it ensures system stability and security. By isolating processes, memory protection prevents accidental crashes caused by faulty programs and ensures system stability. This isolation also enhances security by preventing malicious processes from accessing sensitive data. So there are some techniques for memory protections. First is base and limit registers. So these registers define the range of addresses a process is allowed to access. The base register holds the starting address of a process's memory space, while the limit register specifies the size of the memory allocation. If if a process tries to access an address outside this range, the system triggers a protection fault. Then second is paging and segmentation. So paging ensures that each process operates within its own virtual memory space, isolating processes from one another. And segmentation divides memory into logical segments like code data and stack, further enforcing access restrictions to different parts of memory. Okay. Memory sharing for inter-process communication, IPC. What is shared memory? So, shared memory allows multiple processes to exchange data efficiently by sharing a common memory space. Instead of copying data back and forth, processes access the same memory region, reducing overhead and improving performance. Why it is important? So it enables fast communication between processes, as data is stored in a shared region accessible to all participating processes. It is especially useful in applications that require high-speed communication and low latency, such as real-time systems and performance-critical applications. So, for example, in database systems, shared memory is used for query optimization. When multiple processes need to access or update a large dataset, they can use shared memory to minimize duplication and improve query performance. Okay, memory management in Android. Let's look at a real world case scenario. So, first of all, key techniques to used in Android memory management. First is paging and memory compression for efficient app switching. Android uses paging to lead only to load only the necessary pages of an app into memory. It also applies memory compression to reduce the memory footprint of background apps, enabling smooth app switching. Second is low memory killer. Android implements a low memory killer mechanism to identify and terminate background apps that are consuming too much memory. This ensures active apps have enough memory to function efficiently. Third is virtual memory for multitasking. Android relies on virtual memory to manage multiple applications on limited hardware. Virtual memory allows inactive apps to offload data to disk storage, freeing up physical memory for active tasks. Key insights. So what are the key insights here? We can say that Android's memory management is designed to optimize app switching and multitasking and maximize efficiency on devices with limited hardware resources, and ensures system stability by managing background processes using tools like the low memory killer. Okay, next we'll examine a case study on memory management in cloud environments. So, cloud systems rely heavily on memory virtualization to allocate resources dynamically based on workload demands. So, virtualized memory enables efficient utilization of physical memory across multiple virtual instances. So, virtual machines use virtual memory extensively for isolation, like which ensure processes within one virtual machine do not interfere with another, and scalability, which is dynamically scaling memory resources as workloads increase or decrease. Next is example. So, for instance, AWS EC2, if we consider, so these cloud instances allocate memory dynamically based on the workload. For example, during peak demand, additional virtual memory can be provisioned seamlessly to maintain performance, ensuring scalability and resource optimization. Now let's see Windows memory management. So Windows uses virtual memory to extend physical memory, allowing programs larger than available RAM to execute seamlessly. Then paging ensures inactive memory pages are moved to disk, freeing up physical memory for active processes. Windows implements memory protection to prevent unauthorized access, and it defines permissions. Access control list (ACL) define permissions, ensuring only authorized processes can access specific memory regions. This enhances system security and stability. Windows optimizes memory allocation to support multitasking. By dynamically managing resources, Windows ensures smooth operation of multiple processes without significant slowdowns. Okay, now see Linux memory management. First of all, like paging, it uses paging and segmentation. It uses the combination of paging and segmentation to manage memory. The paging ensures that processes can use non-contiguous memory efficiently, while segmentation helps organize memory into logical units. Linux implements virtual memory by utilizing swap space on the disk. When physical memory RAM is full, inactive pages are moved to the swap partition, freeing up RAM for active processes. Then it supports shared memory to enable fast inter-process communication, IPC. It also uses memory mapping to allow processes to directly map files into their address space, improving efficiency for large file operations. Okay, Mac OS. So Mac OS memory management is known for its efficient and secure memory handling. So it uses paging and virtual memory, so to manage memory by dividing processes into pages and loading them into physical memory as needed. Then virtual memory extends RAM by offloading inactive pages to disk, enabling multitasking and handling large applications efficiently. Mac OS implements memory compression to optimize RAM usage. When physical memory is constrained, inactive pages are compressed instead of being swapped to disk. This reduces the memory footprint while maintaining quick access to data. And Mac OS provides memory protection mechanisms to ensure security. This prevents unauthorized process from accessing or modifying memory regions, enhancing system stability and security. Okay, now this diagram illustrates memory allocation techniques using three methods: contiguous allocation, paging, and segmentation. In this method, in contiguous allocation, memory is allocated in continuous block. So each block A1 to 3 is assigned a fixed portion of memory, shown in blue for allocated memory and orange for free memory. This method can lead to external fragmentation, as gaps of free memory between allocated blocks cannot be used efficiently for larger processes. So paging, as I already explained earlier, and divides memory into fixed size pages, and segmentation uses segments, like it divides memory into logical segments. So these are just showing like in visualizing the three of these memory allocation techniques in one frame. Okay, so basically all Android, Mac, Windows, Linux, all of them have similar processes and steps the computer or the operating system use to operate the system or make it more faster. So so the key takeaways, we can say virtual memory is the key function in every operating system, and techniques like paging and segmentation is also very important in every operating system. And the systems like Windows, Linux, and Mac OS employ advanced techniques such as memory compression, protection mechanism, and virtual memory to handle complex workloads efficiently. So for we can say that memory management is critical for ensuring system performance, stability, and multitasking. By leveraging techniques like paging, segmentation, and virtual memory, operating systems can effectively manage resources, support multitasking, and ensure a seamless user experience. So that is all for today. If you have any question or concern or any other any other inquiry, feel free to reach out to me. You can find a discussion forum for this lecture on Moodle, and you can post any question or any discussion post if you are confused about anything related to this lecture. Then you can have discussion, or I will reply to your questions there, or you can always email me anytime. So that is all for today. Thank you.